Okay, I think when we started to construct things, we were talking about the perpendicular bisector. That was the first thing we constructed. God, I hope I showed you. I showed you the constructions website. So the perpendicular bisector, line segments have it. So the set of all points in the plane equally far from the two endpoints of the line segment. The set of all points in the plane equidistant to A and B. So I should have probably started with that. Given a line segment AB, the perpendicular bisector is the set of all points equidistant to A and B, right? It will contain the midpoint of the line segment, which I consistently miss, and any point here will give you isosceles triangles because of these two distances. Each point on this line, these two distances are the same. And the one of the first constructions is constructing the perpendicular bisector. We just basically intersect circles, right? If you remember, we just open up. Yeah, this is going to be a time killer. We're just going to draw not the whole circle because we kind of know where, right? We kind of know it's going to go here, go through the midpoint. So we just use the same radius. But these crappy looking little thingies are just parts of a circle with the same radius. So because we use the same radius, this intersection point is at that radius distance away from A and from B. And there is this other point here with the same property and 2 points uniquely determine a straight line, right? That's the first construction. And we cannot do much less. So if someone asks, draw a perpendicular line, then you're going to draw a line, pick 2 points, and then construct the perpendicular bisector of that line segment that you're going to ignore and say, here is your right angle. We cannot just do a right angle in isolation, sort of. So that was the first thing. Now I want to run with the perpendicular bisector. One of the first problems that engineers are given is you're given a circle and find the center. And so here is a fun fact. If you have 2 points on a circle, that's called a chord. The line segment connecting, the straight line segment connecting them is called a chord, like the chord of a guitar. And so a fact is that the perpendicular bisector of any chord will contain the center of the circle. It's kind of obvious if you just think about it in a little bit different point of view. For example, you can think of these 2 points as equally far from the center, or you can think of the center as equally far from these 2 points. Well, then it has to be on the perpendicular bisector, right? So one of those first engineering construction problems is you're given a big circle, just draw 2 chords, make sure they're not parallel like this. Just draw any 2 non-parallel chords, construct their perpendicular bisectors, and where they intersect each other, that must be the center, right? Does it make sense that this distance is the radius, this distance is the radius, therefore this point has to be on the perpendicular bisector, which collects the equidistant points. You can see from the picture that if the chord is parallel, then we're just going to keep getting the same line. There is lots of intersection points, but none of them is elevated as the center. It's kind of a cute little fun fact, but it's kind of important. For example, if you have 2 circles that have 2 intersection points, then guess what? Remember that if 2 circles are tangents, then connect the centers, and the point of tangency is going to be there. I guess it's similar. You draw in this is a common chord. So the perpendicular bisector will contain both centers, right? So it's kind of that idea. It's still, when you connect the centers, there's something important happens. So we're going to start with any triangle and construct the perpendicular bisector of 2 of its sides, any 2. So unless the problem says right angle, try to stay away from right angles. Unless the problem says isosceles, try to stay away from that. It's harder than it sounds. All right. So I'm actually going to construct it, but you kind of get the idea. Maybe I shouldn't, but it's kind of fun. But this kind of picture is going to be busy enough for you to understand why we don't draw the entire circle, just the part of it that we use. So I just started to construct the perpendicular bisector of this line segment. So this is the midpoint. This is how you find the midpoint of a line segment as well, by the way. You cannot just find a midpoint. You have to find a perpendicular bisector. And then we're going to rinse and repeat with another side. By the way, because in construction, you know, we miss things. And also the finished picture, you don't really know what came first, what came second. So we usually write down the steps of construction, but it's very time consuming and no fun. You have those videos. So I'm going to omit those. All right. So here is this triangle ABC, and we constructed two perpendicular bisectors. This here is a perpendicular bisector. I'm going to call it L, line L. Is a perpendicular bisector of side AB. And let's call this K. Is the perpendicular bisector of side BC. So far, so good? Now, these two sides are not parallel. So when we construct perpendicular lines to them, they cannot be parallel either. So there is no way these two lines will have an intersection point. They cannot be parallel because they're perpendicular to two lines that aren't. So this intersection point P always exists. It doesn't always have to be inside the triangle, but this intersection point always exists. So let P be the intersection point, intersection of L and K. Ready for the fun stuff? Okay. So P is on L, and therefore, I'm going to first just, P is on L, therefore, these two line segments are equally long. Right? L is a perpendicular bisector. It's the set of all points equally far from A and B. So any point on this line is equidistant to A and B, right? P is on L, so the distance between A and, this is P, I'm sorry. The distance between A and P is the same as the distance between B and P. That's how you're gonna denote distance. It's tiny steps that will take us so far. So now, but P is also on another perpendicular bisector, the perpendicular bisector of line segment BC. So that means that its distance from C and from B is the same. What can we conclude here? Well, these three line segments are all equally long. It's kind of obvious, but both this one and this one are equal in length to this one, right? If x equals to y and y equals to z, then all three x, y, and z are equal to each other, right? That's what's going on. So basically, these three line segments are equally long. So what we can conclude is that AP, this overline means it's the length of the line segment, not the line segment itself. So the length of AP equals to the length of PB to the length of PC. And there are two huge consequences of that. Number one, if we were to draw in the perpendicular bisector of the third side, it would contain this point. So the third perpendicular bisector is also going to contain this point. So the third perpendicular bisector also contains P because P is equally far from A and C. Basically, these two lines are equal to each other because they both are equal to this, right? also contain P. So this is kind of huge. If you have three straight lines, no one is stopping them to do this. Three non-parallel lines in the plane. But the perpendicular bisectors of any triangle don't do that. They intersect each other at a single point. They do this. Isn't that cool? So the perpendicular bisectors of any triangle intersect each other at a single point. And the second fact is that, well, then, if I make this the center of a circle and this length, the radius, that should be a circle that contains all 3 points. All right, it clearly messed up a little bit, but I think it looks believable. So every triangle, no matter how crazy, it's on a circle. And there is this unique circle called the superscribed or circumscribed circle of the triangle. And that's the second consequence. And that exists for every triangle. Let me see this page. Am I ready to share that page with you? And can I find it quickly? Okay. So I'm not going to give you this website just yet, but this is a really cool website. Basically, there is a triangle here that I can drag along. So I'm going to click on show the perpendicular bisectors. There they are. Remember Thales' theorem? So you have a right angle if and only if this point is on the triangle, and then it's going to be the midpoint of the hypotenuse. You see there is a right angle there? Or if you're trying to make, let's make an isosceles triangle with the right angle here. There it is, right? Let's make a right angle here. See, that's Thales' theorem that we did last week. That's a special case, right? Now I'm gonna click on show circumcenter. That's just gonna mark this point, which if I so that is the center of the circle, and then the third one is, well, the circle. And if so, this thing can be inside the circle. If the angle is right, then it's gonna be the midpoint of the hypotenuse, no matter where you make the right angle. And if one of the angles is more than 90, then it's going to be outside of the triangle. The reason I'm not giving you this website yet is that there is other stuff. There are angle bisectors. See, it is an angle bisector. Here's another one. And guess what? They too intersect each other at a single point. And there are also heights or altitudes, which you know very well from base times height over 2. What you don't know is that they too intersect each other at a single point, which is a fun fact. And then there is this thing called medians. A median, and they too intersect each other at a single point. A median is when you take the midpoint of a side and connect it with the opposite vertex. I know I'm throwing a lot at you, but the only thing we're looking at today is the perpendicular bisectors and the superscribed circle. Fun stuff. Any questions?